Alright, one last video with quadratic trinomials, and I want to be really careful here. This is not material that you need. This is purely bonus material for the purposes of our class. But before you turn off the video, if you haven't already, it might be worth sticking around and seeing this because it ends up being kind of cool and gives you some shortcuts that you can apply that might make your life a little bit easier. Before I get going, I have to give you fair warning. The algebra gets really complicated in here. In fact, it's stuff that you probably shouldn't be able to duplicate and maybe not even follow for the purposes of our class. But that's okay. Even if you find yourself lost in the algebra, don't worry about it. If you get lost in the algebra, you can still kind of see the punchline at the end and use the shortcuts that I'm referring to. All right, that feels like plenty of disclaimers. The idea with this bonus material is, in the previous videos, we've taken a quadratic trinomial written in its standard form, and we've applied this method called completing the square to rewrite it so that it's in its vertex form. The motivation for doing so is the vertex form allows us to see each of the different function transformations, so we can apply those function transformations to the graph of y equals x squared to come up with the graph of this quadratic trinomial, which we otherwise would not have been able to graph. In this video, I'm just going to do that exact same thing, except instead of starting out with 2x squared minus 16x plus 30, I'm going to start out with y equals ax squared plus bx plus c. Instead of 2, negative 16, and 30, I'm going to leave constants a, b, and c in my equation. That'll make the algebra especially tricky, but if we're able to transform this into vertex form, and this is the part that I was referring to where you'll probably get lost in the algebra, we'll have some pretty cool shortcuts that you might find make life a little bit easier. So without further ado, if I start out with y equals ax squared plus bx plus c, and I wanted to rewrite it in its vertex form, well, my first step over here was to subtract 30 from both sides. My first step over here would be to subtract c from both sides of the equation. So I guess I'd have y minus c equals ax squared plus bx. Even though there's a, b's, and c's floating around, I've managed to isolate the x squared and the x terms, which is where I'm supposed to be after my first step. From there, I recognize that my completing the square method only works if the leading coefficient is a 1. That is, if there's no number in front of this x squared term. In this case, I have an a in front of my x squared term. So to get rid of that, I'm going to divide both sides of the equation by a. That'll leave the left side kind of ugly, y minus c over a. But on the right side, if I divide each of these terms by a, I'd get x squared plus bx divided by a. I'm now at the stage where I want to add some magic number to both sides of the equation to create a perfect square over on the right side. In order to figure out what that number is, it'll help to rewrite bx over a as b over a times x. These two things are the same because you can view this x as x over 1, which gets you back up here. Anyways, now you're trying to figure out what number you're going to add to both sides of the equation to get a perfect square over here. And maybe you remember that the way you figured out that number is you took this coefficient, b over a in this case, and you first cut it in half. If I cut b over a in half, I get b over 2a. And then you square that thing. So b over 2a squared is the number that I want to add to both sides of the equation. Instead of adding b over 2a squared, it'll make the algebra a little bit easier if I think about b over 2a times b over 2a, producing b squared over 4a squared. So I'm going to add b squared over 4a squared over here, and I'm going to add b squared over 4a squared over here. Now my left side is just a total disaster. Y minus c divided by a plus b squared over 4a squared. But I'm not worried about that. I'm focusing on the right side where I've managed to produce a perfect square. I know it's hard to see that this is a perfect square. It was a lot easier to see that x squared minus 8x plus 16 was a perfect square. But this has to be a perfect square because we've done the same steps to produce it. What is this perfect square equal to? Well, maybe you remember that it's always going to be equal to x plus or minus half of this coefficient. So in this case, it would be x plus half of b over a, or b over 2a. That's pretty complicated algebra, but the good news is now all we got to do is solve for y. The bad news is solving for y is a little bit uglier than it used to be because we have all these constants floating around instead of numbers, but it's fine. First, maybe just subtract this mess over to the right side. That would leave me with y minus c over a is equal to x plus b over 2a squared minus b squared over 4a squared. And then, if I want to get rid of this a, multiply both sides of the equation by a. That leaves me with y minus c equals, my a has to hit this term and it has to hit this term. So I would have a times x plus b over 2a squared minus a times b squared over 4a squared. But I can take the a that I'm multiplying over here and one of these a's in the denominator and cancel those out, and that leaves me with b squared over 4a over here. Finally, I add c to both sides of the equation, and that gives me y equals a times x plus b over 2a squared minus b squared over 4a plus c. I could leave things like this, but I'm actually going to clean it up a little bit, leave this a times x plus b over 2a alone and square that. And then instead of subtracting something and adding something, I want to subtract this entire thing. Let's see, so if I'm subtracting the entire thing, the minus sign has to get distributed to the two terms. So I'd be changing the sign on this guy. What I'd end up with is b squared over 4a minus c. Because if I took this minus and distributed it through, it would get me exactly what I have up here. The reason I did that, put this inside parentheses, is because I want to view this all as one thing. It'll be useful later for transformations to have this all as one thing. That one thing I can rewrite if I find a common denominator. If you think about this c as c over 1, I can multiply the top and the bottom by 4a, and then I would have b squared minus 4 times a times c, and then in the denominator, in both terms, I'd have a 4a, so I can write that whole thing over 4a. You might recognize this b squared minus 4ac as something that shows up in your quadratic formula, and in fact, that's going to be one of the punchlines from this, one of our big takeaways. You might not recognize that. You might have spaced out because this was just ridiculous algebra and there's no way that a student in our class should be able to follow this at this point, and that's totally fine too. We're done with the algebra. We're going to take this as a given. All I'm trying to show you is if you started out with this standard form, the same steps that produced this vertex form from this standard form could produce this vertex form. And you're like, yeah, whatever. Why would I care about that? Well, if you think about what we used our vertex form for above, it was to see the different transformations that we can apply to the graph of y equals x squared. We can now see those transformations, right? What we're going to do is we have this vertical transformation where we multiply all of the y values by a, and we also have this vertical transformation where we subtract from all the y values b squared minus 4ac divided by 4a. We also have one horizontal transformation corresponding with this b over 2a, but because horizontal transformations act in kind of the opposite way that you'd expect, we're going to subtract b over 2a from all of the x coordinates. How is any of that helpful? Well, think about the graph of y equals x squared, kind of our starting spot, loosely speaking. Suppose we want to figure out where the vertex of this graph ends up. Well, let's see. It starts out at 0, 0. Maybe I'll apply my vertical transformations first. My first vertical transformation says multiply all the y values by a. So this y value is originally 0. 0 times a is still 0. And then I have to subtract b squared minus 4ac divided by 4a from that 0. Well, 0 minus b squared minus 4ac over 4a is just negative b squared plus 4ac divided by 4a. And that expression will represent where the y coordinate of the vertex ends up. And the x coordinate is even simpler. We only have one horizontal transformation, and the x coordinate is only changed by horizontal transformations. So the x coordinate of the vertex will always be at negative b divided by 2a. What I'm saying is, if you happen to have this memorized, which I'm not suggesting that you do, but if you had this memorized and somebody gave you this quadratic trinomial in its standard form, instead of going through all the steps that we did to write this in vertex form, you could be like, well, somebody already did all those steps to write it in vertex form in green here, and the big punchline was that the vertex is always going to be at negative b over 2a, comma, negative b squared plus 4ac over 4a. So in this specific case, playing the role of the a is the 2, and playing the role of the b is a negative 16, and playing the role of the c is a 30. So if I want to know where the vertex is, all I have to do is take the negative of b, so the negative of negative 16, in other words, positive 16, and divide that by 2 times a. So 2 times 2, which is 4. 16 over 4 is just 4. The x coordinate of my vertex should end up at 4. What about the y coordinate of the vertex? Well, one way you could figure it out is by taking b and then squaring it, taking the negative of that, adding 4 times a times c, and dividing by 4a. So let's see. b is negative 16. Negative 16 squared, that's getting pretty big, but maybe you trust me that that's 256. So I have positive 256 with this negative, which makes it negative 256. And then to that negative 256, I have to add 4 times a times c. Well, let's see, a is 2, c is 30, so 2 times 30 is 60, and 60 times 4 is 240. So negative 256 plus 240 is negative 16. And then I'll take that negative 16 and divide that by 4 times 2. Negative 16 divided by 8 is negative 2. What I'm saying is the vertex of this polynomial, without converting it into vertex form, should be at 4, negative 2, which matches up with what we saw when we did convert it into vertex form and apply all of the different transformations. And you might be like, yeah, but that sucked. That was terrible to have to figure out b squared and add 4ac. I don't want to do all that arithmetic. Okay, but maybe you agree that this wasn't too hard to find the x-coordinate of the vertex. It was kind of nice to have the shortcut where I could take the x-coordinate of the vertex by taking negative b over 2a. That's not too horrible of a formula to memorize. If you have that formula memorized, instead of using this to figure out the y-coordinate of the vertex, we can figure out that the y-coordinate of any point on the graph I get by just taking the x-coordinate of that point on the graph and putting it into the machine. So I could just take this 4 and plug it into this equation right here. 4 squared is 16 times 2 is 32. Minus 16 times 4 is 64. So 32 minus 64 is negative 32. Plus 30 more leaves me with negative 2, the same answer that I saw up here. Is it easier? I don't know. I mean, I guess it kind of depends on your use case and how much you want to do arithmetic and if you have a calculator handy, but I feel like it's at least worth mentioning that there's ways to figure out where the vertex is without going through all these steps of completing the square. And probably the most common one is just to recognize that the x-coordinate of the vertex will always be at negative b over 2a, where a, b, and c are defined to be the coefficients on the x squared and the x term and the constant term, respectively. One more thing before I end this video, because I think it's kind of cool. This was just all about the vertex, but what about the x-intercepts? We saw up above that the x-intercepts, after we transform this into vertex form, were at 3 and 5. And that we figured those out by just figuring out, well, we cross the x-axis whenever the y-coordinate is 0, so we take our function and we set it equal to 0 and solve. But look what happens if we take this form and set that equal to 0 and solve. We would have 0 equals a times x plus b over 2a squared minus b squared minus 4ac over 4a. If we want to get at this x, our first step would be to move all this stuff over to the other side of the equation. So I would have b squared minus 4ac divided by 4a equals a times x plus b over 2a squared. Our next step is to get rid of this a. So we divide both sides of the equation by a. That gives me b squared minus 4ac divided by 4a squared. And that's equal to x plus b over 2a squared. If I want to get at this x, I better get rid of these parentheses. To get rid of these parentheses, I take the square root of both sides of the equation. You have to be careful when you take the square root of both sides of an equation. You got to put in the plus or minus. So I got plus or minus the square root of b squared minus 4ac divided by 4a squared, which is equal to x plus b over 2a. But if you're comfortable with how square roots work, the square root of a fraction is the same as the square root of the numerator of that fraction divided by the square root of the denominator of that fraction. So really what I have is plus or minus the square root of b squared minus 4ac divided by the square root of 4a squared. That's equal to x plus b over 2a. Well, a nice thing happens over here in the denominator. 4a squared is a perfect square. 2a times 2a gives me 4a squared. What that means is the square root of 4a squared is just 2a. So I can rewrite the left side as the square root of b squared minus 4ac all over 2a. All of a sudden that might be looking really familiar, something maybe you memorized in a previous class. To get this x all by itself, subtract b over 2a from both sides of the equation, and what we're left with is x equals negative b over 2a plus or minus the square root of b squared minus 4ac all over 2a. Wait a minute, I got two fractions that have the same denominator. Couldn't I combine those all into one fraction? Yeah, you sure could. wouldn't that leave me with negative b plus or minus the square root of b squared minus 4ac all over 2a? Yup. Really, all the quadratic formula that you probably memorized in a previous class is the solution to the x-intercepts that you get if you take this version, this vertex form of the quadratic trinomial ax squared plus bx plus c. Typically, you're presented with this with no context at all for how to find the roots of a quadratic trinomial. But with the knowledge that we've gained in this section, we don't need this formula given to us. We can derive it using these same methods of completing the square, even though the algebra gets a little bit intense and a little bit crazy for our purposes. But that's why I called all this stuff bonus material. You don't need any of this stuff. However, if you want to find the vertex, there's this nice little shortcut for finding the x coordinate and the y coordinate of the vertex. And FYI, that quadratic formula that you memorized way back in the day is really just a direct result of completing the square on this general quadratic trinomial. Kind of cool, I think.